Welcome to JavaScript the Hard Parts here at Codesmith, or here in my office. If you have never been to Hard Parts before, or this is your first kind of interaction or experience with Codesmith, welcome. It's nice to meet all of you. My name is Samantha. There's a little slide about me coming up, but basically I'm the lead engineer at Codesmith. I also do some teaching in our LA immersive program, and I teach workshops like this because I love doing this stuff. So yeah, again, if this is your first time at Codesmith, this is a software engineering residency. We have campuses in both New York and Los Angeles. We also have a part-time remote program, which just kicked off a few weeks ago, 1 week ago, a week and a half ago or so. So we have those kinds of programs. If you're interested or have been looking around at different boot camps or different engineering programs, we are one of those. We also have some other programs that I'll talk about in a little bit that are more like preparatory programs. If this is kind of, you're just getting started with JavaScript, or you're not really quite feeling like ready for a 12-week immersive program or a 39-week remote program, we have some other options as well. So what we do here at Codesmith is we teach software engineering, right? We don't teach people how to be technicians. What we do is we teach people how to be engineers. So our lectures and our style of teaching here at Codesmith is maybe a little bit different, and the way that we're going to go through this workshop today is maybe a little bit different from other workshops that you've been to. This is not a kind of code along tutorial style workshop. We're not a kind of code along style, tutorial style bootcamp. Those things have their place. Those things have those things are really great for when you're first starting out, to kind of just get a hand in and a guided kind of walkthrough on how to do something and how to write JavaScript and things like that. But when you're actually trying to work in the industry, work in the field, when you actually go out there to get that software engineering role, what people are looking for is more than just a technician, right? They want to see that you can solve problems with code, that you can look at a problem you've never seen before and solve it with code. And so that's what we do here in our immersive program. We do that in 12 weeks. In our remote program, we do that in 39 weeks. I see somebody in the chat. The part-time or the remote program right now is part-time, so it's not a full-time program like our on-site program is full-time. So our on-site program is 12 weeks. It's 6 days a week, and it's 9 to 8 p.m. 6 days a week, except for Saturdays, it's 9 to 4. Our remote program is a little bit longer. It's extended out because it is part-time, so it's not every day of the week, and it's not as many hours during the week. So it's expanded out over a little bit longer of a period of time. So anyway, what else do we do here at Codesmith, right? We not only prepare you for the job search, but we also have a hiring network and a hiring program that helps you go through and craft your resume for a technical resume. You go through mock interviews and whiteboarding practice. Technical interviews are a thing that is maybe a little bit different from anything you've done before in terms of interviewing for jobs. So we prepare you for that as well. And the way that we teach here at Codesmith, like I mentioned, is not a walkthrough, is not a guided tour of software engineering, right? We're really trying to teach people how to be engineers, how to solve problems with code. And we do that through teaching in a pair programming style and doing kind of hard learning, right? So the types of things and the way that we're going to be teaching and learning tonight is that hard learning, right? We're not just going to kind of sit and code along together. We're going to walk through how the JavaScript engine actually runs our code, what's going on under the hood of our code when we run it, so that we not only know how to write. Tonight we're talking about async and promises, how to write asynchronous code, but also how it's working and why, when things go wrong and things don't work as we expect when we write this type of code, why that might be and how we can better debug that. So we do that through pair programming, a lot of pair programming. We have other workshops where you get a lot of practice in that pair programming experience. So this is the team that makes it all possible. We have from our CEO and co-founder, Will Sentence. He does a lot of these workshops as well. If you're brand new to Codesmith, I'm sure you will see him around the next time you come around. All the way through, we have me there, lead engineer, right? We have our lead instructor, Shane, who is the lead instructor of our new remote program. We have Shanda, who's our director of admissions and outcomes. So somebody walking you through both coming into the program as well as coming out of the program and helping in that job search. And then along with a slew of other team members, like our lead technical mentors, people giving instructions in our core curriculum, engineering fellows that are there to help with pulling you out of those ruts, right? When you get stuck in your code, as you're pairing through things and you're really stuck and you're not sure where to go from here, we have other people on the team that are there to pull you out of that, help you, get you back on track, right? And then a huge alumni network that's out there to help grads get jobs, right? And give a network of support in that job search as well. If you are looking for a program like Codesmith, these are a lot of the outcomes and things that people want to see, the types of numbers, right? Number of graduates per year, percent of them hired within 180 days, the median starting salary, those kinds of things. All of these other kinds of metrics and statistics you can find more details about on our website, as well as on CIRR or CIRR is a third-party audited results. Those are all kinds of things you can find online. Please take a look if those are the kinds of things that you're interested in, which, you know, they should be, right? And over on the other side here, we have some of the companies that some of our grads have been at. And really what we're talking about here is the kind of level of engineering work that grads coming out of our program are getting, right? We have grads going and getting mid, senior level software engineering roles. And that's awesome. The salaries are obviously great. It's a good factor to look at when you're looking at programs, but it's also indicative of the type of work that you're going to be doing, right? The types of engineering problems and challenges you're going to be solving. So what is the admissions process like for a program like this? We have an online application, right? And you can complete a coding challenge and answer some questions about your programming experience, things like that. For coming to this workshop tonight, you do get a fast track application code that lets you bypass the essays and also guarantees you an interview. We then have a non-technical interview, and you know, kind of just getting a sense of why you're interested in Codesmith and your background and your goals and things like that. And then we do actually also have a technical interview because we are building out a community of engineers. There are a lot of different, oh, hold on one second. Sorry, there's a lot of questions here. Are the slides changing? Yes, the slides are changing. I'm scrolling down through the slides. You should be able to see news. So you should be on a slide or be able to see a slide that says admissions process. Is that what you guys are seeing, or are you seeing something different? Nope. Okay. Let's see. Is that better? Aha. Okay. There we go. Not sure why the sharing got paused. Okay. Well, in any case, we've gone through a couple of these slides. You'll get these slides afterwards anyway, so feel free to kind of go back through. These are the outcomes that I was mentioning, right? In terms of graduates and percent of them hired and median salaries and companies and things like that. You'll get all these slides, like I mentioned, afterwards, and I'm happy to stick around afterwards and chat about any of these things if anybody has questions. Awesome, thanks, sorry about that. Okay. So we have this technical interview, right? And part of the reason that we have this technical interview is that we do want people coming into the program to have a bit of a baseline level of knowledge, right? We want everybody to be starting from some baseline level of knowledge. And then we want to also make sure it's not just about how much code do you know, how much JavaScript do you know, but it's also about seeing how you're going to work in a pair programming environment, seeing how you're going to work in this community environment. A lot of what we strive for here at Codesmith is building up everyone together so that you're kind of with your cohort of other engineers and you're all working together to kind of build cool stuff and build really great projects. And that's only going to help you in that job search, because the thing that sets apart mid and senior level engineers from junior engineers is not only the ability to solve problems with code, but also the ability to communicate your solution to those problems. So we have a huge emphasis on pair programming and technical communication and analytical problem solving, because those are the things that set people apart in those mid and senior level roles. And then we have decision and financing after that technical interview. And that's where we can start talking about things like scholarships and financial aid and things like that. We have a ton of different scholarships, a ton of different financial aid opportunities and financing opportunities. So that's another thing that we can talk about. So how can we prepare for Codesmith? It is the Codesmith immersive program. It can sometimes be a little daunting to think about, okay, I have to come in and do a technical interview. There's a lot of things that can go into that. If you're brand new to coding, we also have some other part-time and prep courses, ranging from very, very beginner level prep courses like JavaScript for beginners to something like CS Prep. That is a kind of guided 2-week prep program. It's again, sort of part-time, right? Monday, Tuesday, Wednesday, and then all day on Saturday for 2 weeks. There are scholarships and rollover tuition options available for both of those as well. And in terms of preparing with free resources, we have workshops like this, obviously, and then we also have CSX, which is our online learning platform, similar to some of the other kind of online learning platforms out there, but really going through and teaching concepts in the same style that we teach them here at Codesmith. A lot of the units follow with different concepts, or follow the different concepts that we teach in these free workshops. So feel free to kind of check that out. We also have a Slack channel that goes along that, where a lot of the community members will post their solutions, help each other out. It's a great way to also network and find pair programming partners, find just other people to hang out and code with. So highly recommend checking out either of those resources. And then what we look for in candidates. All of this up till now was kind of things that you might be looking for in a program, things that you might be interested in doing to prepare for a program like Codesmith, but there are also things that we're looking for in our candidates. And like I mentioned before, right, analytical problem solving and technical communication are obviously those first two things that we're looking for. Those are the things that set you apart when you're going and looking for those senior and mid-level software engineering roles, right? Then engineering approach, right? How you handle not knowing things, how you debug through your code, what your code structure looks like, how you read through documentation. Do you reference documentation when you're unsure of something? Non-technical communication, this is, I like to call this the don't be a dick rule, right? Which you can know a lot about code, you can have a ton of programming experience, you might have great analytical problem solving skills, but if your delivery of that, of those problem solving skills, if your delivery of that approach, or you have an inability to work with another person on code and in code, right? If you're kind of just generally not going to be a great community member, that's also something we're looking for, right? We want to have empathetic engineers, right? Where if you're sitting with somebody who's maybe not picking up a concept as quickly as you, are you taking that time to sit with that person and help them work through it? Same thing, when you're working with somebody who's maybe picking up those concepts a little bit faster? Are you making sure that you're kind of reaching out for help, right? And saying, hey, I'm not really understanding this. Can we slow it down a little bit? And not getting, overly frustrated and super, throwing chairs, right? And then finally, fifth in line here is JavaScript and programming experience. And I like to highlight this one as the fifth thing on this list. This is an ordered list here. And JavaScript and programming experience is something that we definitely look for. There's a baseline level of understanding that we want people coming into the program to have, right? We want everyone starting from some baseline, but anything above that baseline is honestly a nice to have, right? It's great if you have prior programming experience. It's great if you know a lot of JavaScript already, but it's not something that's going to get you that huge leg up in terms of coming through that technical interview or coming into the program, because these other factors are what really set you apart in that job search then, right? So just because you have a lot of programming experience, right? If you can't communicate that effectively, or if you can't apply that knowledge to problems that you haven't seen before, that's not going to be as helpful for you, right? So all of that's to say, my computer locked. Okay, all that's to say, here we are at Codesmith, ready to talk about async, promises, and the event loop, right? Awesome. Is this switching? Or is it still now stuck on what we look for in candidates again? Stuck again. Sweet. Pause. Zoom. What a bummer. Sorry, everyone. Technical difficulties this evening. Okay. Now we see it. Yes. All right. I will not let the slides freeze again, hopefully. Awesome. So before we dive into all of this content for today, I just want to get to know at least a couple of you. There's a ton of people online tonight. So we're not going to go around and do the entire room, but I'm just going to shout out a couple people. And if you guys can give me your name, if you've been to Codesmith or Hard Parts before, how many times you've been here roughly, and then a JavaScript resource that you've been using lately. So how about Joseph?
Hi, can you hear me?
Yep.
All right, cool. Hi, I'm Joseph. I've been going to Hard Parts for about 3 weeks now.
Sweet.
Yeah, and resources I use is CSX and Free Code Camp.
Awesome. Yeah, Free Code Camp's great. Awesome. Thanks, Joseph.
Thank you.
How about Bren?
Hey everyone, can you hear me?
Yep.
Cool. This is actually my first Hard Parts, so I'm super excited about that.
Woo, welcome.
Yeah, thanks. And resources I use currently are LeetCode and CSX.
Nice. LeetCode's always great for some algorithm challenges. There's a ton of them out there. LeetCode's my favorite though. I don't know why. Just kind of finding your flavor of ones that you really like. Awesome. How about Vanessa? Oh, Vanessa, maybe I'll come back to you. Peter.
You hear me?
Yep.
Awesome. My name's Peter. I'm coming from Connecticut, or I'm tuning in from Connecticut. Great state, awesome time. I use currently CSX, and I've taken a couple of Udemy courses in JavaScript. And I was at a recursion Hard Parts, I think last week or a couple weeks ago. I can't remember, but second one.
Awesome. Great. Welcome back, Peter. All right. Cool. So now that we are getting ready, oh man, I did it again. Now that we're getting ready to start, I just want to reiterate the thing that I said earlier. So this is an interactive workshop. So if everyone could please update their name in Zoom. Thank you. Shout out to the person in the Zoom chat that that shot the note on how to do that. If you go to participants and click on the 3 dots next to your name, you can change what your name displays as. And so if you are if you don't have a mic and you can't be called on, right? Please put in with your name no mic so that I don't call on you. If you don't have video but you do have a mic and so want to be called on, please just put no video, right? So that I still call on you. If you don't have your video on, I'm going to assume that you do not want to be called on. So please put no video if you just have no video and can't be called on, or can be called on. Sweet. Other than that, if you are going to be called on, please put your name, your actual first, maybe last name, but actual first name in the or whatever first name you want me to call you by in the as your Zoom name, because it makes it easier for me. Sweet. All right. That being said, let's get this show on the road, everyone. Here we go. All right. So we're going to talk about promises, async, and the event loop tonight. Promises are awesome. Let's just start off there. It's going to take a little bit for us to get to that point of talking about promises, but I promise you it's going to be worth it, right? We're going to build up to why promises are even a thing and how much more helpful they are to have than some of the other ways that we've previously done asynchronous activity in JavaScript. So a thing to be clear about at this point, right, is that asynchronicity as a concept is a thing that we were able to actually do well before promises in ES6, right? We were able to do things asynchronously that were not blocking the main thread before we ever had promises. Promises provide us a lot of really helpful syntax and understanding in JavaScript that something is happening asynchronously, that something is happening outside of the regular JavaScript execution, right? So we're going to talk about why they came about, why they were a thing. We're going to introduce some new pieces. If this is, you know, if you've been to hard parts before, but you've never been to this hard parts before, we're going to introduce some new pieces of our diagramming. If this is your first hard part, welcome. It's going to be a great journey. Don't worry, we're going to start off just getting everyone set up on a baseline of the way that we communicate at Codesmith, the way that we talk through our code here. We're going to set that up right now. So before we dive into this asynchronicity and why we care about that, let's set up basic JavaScript, right? Let's talk about the way that we run JavaScript outside of asynchronicity, right? So we have some regular JavaScript principles anytime we run any sort of JavaScript file, right? Anytime we're programming in general, very basic definition of what we want to do here is store data and run functionality on that data at some other point in time. So with JavaScript, we have a way of doing this where we can store variables and we can store instructions, right? So keywords like const, let, var, they all tell the JavaScript engine, okay, we want to store some variable, some data, right? And then this function keyword tells us that we want to store instructions to run on data, right? But instructions that we can reuse over and over and over again. And JavaScript, you may have heard, is single-threaded, which means that we can do one thing at a time in JavaScript, right? JavaScript starts executing, right? If this is our JavaScript file that we're going to be executing, it runs that code line by line, and it stops at each line. It pauses its execution at each line and evaluates each line individually before moving on to the next one. It can do one thing at a time. It is single-threaded. And then when we see keywords like const and function and places where we want to store data for later on, right? Whether it's storing variables or it's storing instructions that we want to run later, right? Groups of functionality, we need some memory space to store that. So when we talk about this particular file here, we're going to go through and talk about the different ways that we're going to diagram this here. So we said that anytime we start running functions in JavaScript, right? Or anytime we start running files in JavaScript, we get a place to run our code. So we get a global execution context. This is just the space that we're going to run our code in. And we get this thread of execution that runs through our code line by line, right? This is how we're going to represent that thread running line by line and executing line by line through our code. We also get a global memory space, a place where we can store data, access that data later on, and perhaps run some functionality on it, right? So we get a global memory space. And then we start kind of running through our code line by line. So, Joseph, tell me, what's the first thing that this JavaScript thread of execution is going to do when it starts running our code?
The first thing, the line 1 is going to be a constant named num, and is assigning the value of 3.
And where are we going to store that?
Inside the global memory.
Yeah, exactly. So in our global memory, when JavaScript hits this line here, right, const num equals 3, it's going to say, okay, we're going to open up this space in our global memory. We're going to give it a label. That label is going to be num, and the value is going to be 3. So anytime we reference the label num, we're gonna return the value of 3 from our global memory. Awesome, thanks, Joseph. What's gonna happen on our next line? Kate.
We declare function called multiply by 2 in global memory, and we store function definition.
Absolutely.
In global memory.
Absolutely. Thanks so much, Kate. So when we hit this line here, right, that function keyword tells JavaScript we're going to store a function definition, right? We're not executing this function. We're not going to run this function. We're going to take all of these instructions, right? This whole set of instructions here, and we're going to store it under this label multiply by 2 in our global memory, right? So we're going to represent that whole function definition because I don't want to rewrite it over again, right, as just this little function definition icon. Awesome. What's going to happen on our next line? Peter.
We're going to create a constant with the label output, and we're going to store the result of the value, or instantiating the function multiplied by 2 with the argument num.
Yeah, so we hit this line, right? Our thread hits this line, const output equals multiply by 2 with this argument of num, right? And so JavaScript sees this const keyword. It says, okay, I know I'm gonna need to store a variable in our global memory space. It's gonna have a label of output, but its value now is a little bit murky, right? We don't have a clear value right off the bat. So we need to figure out what multiply by 2, invoking multiply by 2 with an argument of whatever this num is, evaluates to, right? So for right now, when JavaScript first hits this line, when the thread first hits this line, it does open up a space in global memory. It creates this variable with a label of output, but its value for now is going to be undefined. We can define it, and we will define it by invoking this multiply by 2 function and passing it the argument of whatever num is. And so tell me, Peter, what is num right now?
Num is 3, as you previously stored it in global memory.
Yeah, so what we're actually going to find is the value of multiply by 2 with an argument of 3. And so this is where things get a little interesting, because now our JavaScript thread is here. All right, we've come down here, we've hit this line, and now we need to actually invoke or execute this multiply by 2 function. And since JavaScript is single-threaded and can only do one thing at a time, while it's executing this multiply by 2 function, we're not going to do anything else in this global execution context. So we actually create a new execution context specifically for this function invocation for multiply by 2. So now we get a new function level execution context and a new function level memory space. And that same global thread, right, that same thread that was out here in our global execution context is actually going to move inside the function level execution context for output, or for multiply by 2, right? Meanwhile, we're not moving on in this global thread. It's paused out here in this global thread. And we can start seeing, before we dive into the execution of this multiply by 2 function, right, because we know that functions can invoke other functions inside them. And anytime we invoke a function, we create a new function level execution context and function level memory, and our thread moves deeper and deeper inside those execution contexts until we eventually return. So we're going to introduce one other piece for right now of this diagramming, which is the call stack. So the call stack is going to keep track of where our thread is at any given point in time. So right now, we started out in our global execution context. And then our thread hit a line that invoked another function. And so it invoked multiply by 2 with an argument of 3. And that call got pushed onto our call stack. So our call stack is just keeping track of where our thread is at any given time. What execution context is our thread currently running? And it's just a helpful way to keep track of where we're at any given point in time. So our function level execution context starts running. The first thing that we do in any function execution context is handle our parameters. So we have this parameter, the argument 3 was passed in, and we said in our function definition here that we're going to give that a label of input number. And the value is going to be whatever value gets passed in. That's going to be 3. And then we hit, the first line of running this multiply by 2 function, which is going to be const result equals input number times 2, right? And as we know, input number is 3. So this is going to be 3 times 2, which is going to be 6, right? So in our function level memory, we have now a variable with the label result, whose value is 6. And then we get to the last line of this multiply by 2 function, which just says return result. In this case, result is 6, right? So we actually return 6 out of this function. So tell me then, a couple of you don't have names. If you've got your video on and you don't have a name, throw your name in the Zoom so that I can call on you. How about Bren? What happens when we return out of a function in JavaScript?
We actually close out the current execution context that we were in and delete it out of memory.
Yeah, so we close that function level execution context, right? Our thread then moves back out to whatever the prior execution context was, and we can track that in our call stack, right? Because when we return out of a function, that function call gets popped off our call stack, and we return to whatever the prior execution context was, right? Which in this case was global, so our thread returns out here. We also, though, in this case, right, Bren, we returned a value. Where do we store this value that we returned out of this function?
We return that to output, which is in global memory at the moment.
Yeah, we said originally that we were going to store whatever the output of invoking multiply by 2 with the argument of 3 was in this label output. So now, once we have a returned value, we can actually do that, right? So output, instead of being undefined, is now 6. Awesome. Then there's still some more to run out here in this global execution context, right? So what are we going to do on our next line here then? Is it Phaton? You there? Okay, I'm coming back to you. You're muted. Coming back to you. Let's see here. Who's got stuff? Tyler? Oh. You're not muted, but I can't hear you. Come back to you then. Yevgeny?
Okay. Let's see. So result was passed down. It was stored in output. So we're now in the next line, which is new output. We're declaring that variable. Well, actually not a variable. It's a constant. And then we're going to initialize it to the return value of the function call of multiply by 2 with the argument 10.
Beautiful. Yes. So in global memory, right, we now open up a new space in memory for not new, but new output, right? New output. And we do need to invoke this multiply by 2 with an argument of 10 to understand what, or to know what actual value is going to be stored here. But for now, what value is new output going to be?
Undefined.
Undefined, right? We don't know yet. So what happens then? Walk me through everything that happens when we invoke multiply by 2 then.
Okay. So then we're gonna create another functional executional context, and it's gonna have its own local memory local variable environment, and the argument will be passed down to that environment. And so num, which is the parameter name, it will be set to 10, which will be held in the variable environment.
Cool. 1 second. What else happens to our call stack?
Oh yeah, so that gets pushed onto the call stack.
Yeah, the call to multiply by 2 with an argument of 10 gets pushed onto our call stack, right? Let's remember that this one is completely gone, right? It was popped off before. And you're exactly right. When we start actually running this function, because our thread enters this function level execution context, when we actually start running this, the first thing we're going to do is handle this argument that was passed in, right? So input number is going to be 10. 10. Awesome. Walk me through the rest of this then.
Okay, so then we're gonna run the code block that's defined in the function, and so the next line would be we'll be declaring a constant, which will be initialized to input number. Oh, okay, so the parameter name is actually input number. But anyhow, input number multiplied by 2, the result or the evaluation on that.
And what are we going to store that as? What's the label that we're going to give that?
Result.
Yeah, so result is going to be the result of input number times 2. And what is input number right now?
Input number is 10.
So 10 times 2?
20.
20. Awesome. And then what are we going to hit?
And then we're going to return that value, return result. And so
result is
20.
Sweet. What are we going to do with that 20 that we return? So
that's going to go into a global space or global well, it's not going to go into global memory, but it's going to go into what the global execution context, and then it's going to be returned to a new output.
Yep. So it's going to be stored in global memory under the label new output, right? And then what happens to this function level execution context?
It gets deallocated.
Yeah, so it goes away, our thread moves back out into our global execution context, and we know that because that function call gets popped off of our call stack, right? Sweet. And then back in our global execution context, we are now done. We have nothing else to run. And so now all of this kind of gets, wiped away. But that's what our code is doing when we run it line by line. Every JavaScript file that you run, line by line, these are the key components that are happening, right? We start out in this global execution context. Our thread of execution starts running that code line by line. Anytime we invoke a new execution context or a new function, we get a new function level execution context. That new function level execution context or function invocation gets pushed onto our call stack so that we can track where our thread is at any given time. And we have these memory spaces where we can store variables that are either scoped locally to that function level execution context or stored globally in our global memory available to any lower level functions that invoke them. Great. This is all well and good, right? This is a great system until we get to something like Twitter, right? Or some sort of modern web browser where we want to be able to do things in the background while we go and fetch more tweets, right? Something like infinite scroll doesn't work unless we have the ability to do multiple things at the same time, right? Because think about what it means for JavaScript to be single-threaded and to be able to do only one thing at a time. That means that if we're scrolling through Twitter and we get to the bottom and we want to load more tweets at the bottom of our Twitter feed, we need to go and get those tweets, and that's some amount of JavaScript that's going to execute a function to grab those tweets from our Twitter account or from the back end of our Twitter service and get that data from our database, right? While that's happening, if we're only working in the confines of what JavaScript allows us to do, which is one thing at a time, we'd have to wait for those new tweets to come back before we could do anything else, right? So think about being on Twitter and think about getting to the bottom of that page and having to load more tweets. While you're waiting for those new tweets to load, maybe you start rereading some of the tweets you kind of overlooked as you were just scrolling and scrolling and scrolling. And you say, oh, I actually really like this tweet. I'm gonna favorite this tweet. And you go and you do the little double click, and what you expect, right, is that little heart to show up, be a little red heart there saying, like, oh, I've liked this thing. But if JavaScript is already out there grabbing other tweets, and it can only do one thing at a time, you double clicking that, that tweet is not gonna actually work, right? We'd have to wait until those tweets came back, and then you might see that jittery heart back and forth, right? Being filled in and then unfilled in because you've now clicked it like 6 times. And we had to wait to actually execute those functions until that JavaScript thread was clear. So this is a huge problem, right? But somehow we've managed to overcome it because clearly Twitter works. Clearly all of these other programs and applications work in infinite scroll and work, and you're able to do multiple things. Users are able to continue to interact while we're doing things in the background. So we clearly have some ability to do something asynchronously, right? To do things outside of the main thread. But just to highlight this problem, right? And really what that feels like to a user, if we didn't have this ability, let's go through what this actually looks like if we're saying that this display tweets function here, let's say that this display tweets function is declared somewhere above this, right? And it does all of this work synchronously, right? Or not display tweets, sorry about that. This get tweets function is declared somewhere else, and it has this ability baked into it to just grab these tweets, and it's going to be synchronous, right? If we do that, what we're going to see here is something along the lines of, you know, we'd have tweets here in our global memory. It'd be undefined at first, right? We'd start out in our global execution context. Then we'd see this get tweets function, right? We have a URL there, and we would open up a new execution context for this, right? This is going to do some amount of work, right? Get those tweets. We'd get that call pushed on to our call stack, meaning our thread is coming down and actually going into this execution context here. And while this is executing, we're just waiting for a long time, right? 350 milliseconds, in fact, let's say, right? And that might not seem like a long time to us as humans. We're like, yeah, okay. But there's a ton of research out there and a ton of literature out there on how quickly your application needs to respond to keep people engaged. People leave if your application doesn't respond in like 0.5 seconds or something like that. It's some insane amount of time that you would think like, whatever. Thinking even back to 10 years ago, it doesn't feel like, it feels like, oh my God, where things happen so fast. But the quicker that we are able to load things, the more likely people are going to stay on our page and continue interacting with it. So if we had this get tweets function that's doing everything asynchronously, kind of now just vamping, because this is how long it actually feels. This is how long 350 milliseconds feels for a computer process, for a computer program, right? This is a long time to wait for something to happen. So now let's assume we got back our tweets, and let's say that this function returns out, it looks like, right, based on this URL down here, we're looking for just a single tweet. And so let's say we get back the string hi, right? That's our beautiful tweet that we just waited all of that time for. Okay, well, now that we're actually out here, now we can, you know, pop this off the call stack. This goes away. Now we can actually invoke display tweets. And we're going to pass in, right, this string hi. Display tweets, again, has some function execution context. Display tweet, right? And maybe over here it does some sort of console log. And so at some point in time, we see hi here in the console log, or in the console. This is okay, right? It works, does the thing. But then we have another console log here, right? Another console log. And this one says, I want to run. And in this case, this console log here has nothing to do with getting tweets or displaying them, right? This is something that is completely separate from these other functions. And it would be really nice if we could just run this console log even before our get tweets finishes, because it's not really relying on any of that information to run. So we have a couple of things here that we'd like to accomplish, and doing this synchronously doesn't really accomplish them, right? Because we'd have to wait a pretty long time before we see I want to run in the console. So the goal for tonight, the problem that we're going to try to solve, and the problem that we're going to solve a few different ways tonight, is this problem of how do we still be able to do long tasks, things that take a long time, like getting a bunch of tweets, like waiting a certain amount of time before, delaying some sort of functionality. We still want to be able to do those tasks that take a long time. We also want to be able to delay some functionality until after that long task is completed, right? We want to know that we have our tweets before we run the display tweets function. But the third thing we want to accomplish is that we don't want to block other things from running while we're waiting for that long task to complete. So that's kind of the main overarching goals of asynchronicity, right? We still want to be able to do stuff while we're doing long tasks, but then we also want to be able to delay some amount of functionality that's reliant on those long tasks being done. So again, before we had promises, we had the ability to do things asynchronously. We could delay functionality using something like a set timeout, right? For those of you that have your video on, or if you don't, throw it in the chat. Feel free to throw it in the chat. How many of you have used set timeout before? A couple of you, right? Or seen set timeout, right? Even looking at it here, it's probably pretty self-explanatory what kind of the goal is of a set timeout, right? We want to set some sort of timer and then run some functionality knowing that that timer has passed, or that amount of time has passed. But a lot of people run into issues with set timeout because they don't fully understand how set timeout actually runs and how it's actually being executed. Because think about that goal, right? If you know how JavaScript works, and we now know how JavaScript works, it runs line by line, it does one thing at a time. Set timeout looks, by all intents, by all appearances, like just any other JavaScript. So we assume that it runs the same way, right? JavaScript does one thing at a time. So we'd kind of expect that these console logs would be something like hello and then me first, right? If we're looking at this example code here. Because if we think that set timeout works the way that regular JavaScript works, we'd be blocked at this set timeout line until 1,000 milliseconds has passed. Then we'd run this delayed functionality, which would invoke this console log. So we'd expect to see hello first. And then once that's all run, then we'd expect this console log me first to show up, right? If we were looking at this as regular old JavaScript, that's probably what we would assume. However, it's actually not how set timeout works, because set timeout uses this asynchronous ability, this ability to do some long task, push off delayed functionality until that long task is done, but also not block our main thread from executing things that don't rely on that long task being done, such as this console log, right? We could also maybe assume that me first is going to run first because of the name, right? If we were just looking at this. But what about something like this delay of 0 milliseconds? Now this is something, right, that gets a little bit interesting. If we know that set timeout allows us to delay this functionality and push off this deferred functionality while not blocking our main thread, it can get extra confusing when we get to something like a 0 millisecond timeout, right? Because in this case, then we might say, okay, well, we hit this line, we're waiting 0 milliseconds. So now we, for sure, obviously, must be running this print hello function first, right? We'd run this print hello function. And so now in this case, when it's 0 milliseconds, when we're not waiting at all, surely we'll see hello and then me first, right? But as we'll see in a second when we diagram through this, again, that is not the case. Still, even if we have a timeout of 0 milliseconds, we are still going to see me first and hello second, because the rules of how set timeout works are the same regardless of what our wait time is. And it turns out that we might not see this hello at the exact time that we put our wait in. So to be able to really understand how this works and what pieces of this code execution we're missing, we need to know that our code is executed not necessarily just in JavaScript, particularly when we're talking about asynchronous code. When we're talking about being able to do more than one thing at a time, we are probably talking about, at least partially, a world outside of JavaScript. So core JavaScript has 3 main parts. Those 3 main parts we've already talked about, right? A thread of execution, a memory or variable environment, and a call stack, right? But we need to add some new components to be able to understand how this asynchronous bit works. The thing we're going to talk about tonight, or a bunch of the things that we're going to talk about tonight, but one of the things we're going to talk about right now is the web browser API. So when we're running our JavaScript code, it runs, for the most part, there are backend, there's Node and stuff, but for a majority of JavaScript is run in the browser, right? Chrome, Firefox, Safari, other ones. And the browser is made up of way more than just a JavaScript engine, right? It can parse through HTML and CSS and does a lot of other things outside of running JavaScript code. And so something that our browsers expose to JavaScript is this web browser API. It exposes this functionality to JavaScript so that JavaScript can basically pass off these long tasks to the browser and say, hey, this is a task that I don't want to be blocking my JavaScript thread. Do this task out here in the web API, and then just let me know when it's done so I can run some delayed functionality back in JavaScript, right? So we're going to introduce this web browser API piece, right? There's a few different APIs and functions that we can run that involve this web browser API. So we're going to talk about a few of those. And then we're going to talk about how we also bring that code back into JavaScript, right? Because not only do we want to pass off that task, but we want to bring some delayed functionality back into JavaScript once that long task has completed. So enough talking. Let's look at how we're going to do this and let's talk through it. So here we go. This is the same code that we just looked at in the above with the set timeout, but let's walk through it line by line like we are regular old JavaScript. All right, let's try this again. Kate, what are we gonna do on our first line here?
We declare function print hello in global memory and store function definition.
Absolutely we do. What do we do on our next line? Keep it going.
And we invoke set timeout.
Awesome. And what happens when we invoke set timeout? Looks like a function, right? What arguments do we pass it?
We pass in function definition print hello and argument of 1000 millisecond.
Yeah, and an argument of 1,000, which in this case is 1,000 milliseconds. And so, Kate, this looks like a regular JavaScript function execution, right? Function invocation. What happens when we invoke a regular function in JavaScript?
We have a new function level execution context.
And we do what with the call stack?
We push set timeout on the call stack.
Yeah, and then we would expect, right, that our thread moves into that function level execution context, and we'd kind of sit there and wait for set timeout to do whatever it does. And at some point we'd be done running set timeout and we'd come back, right? However, this is where we're going to introduce this new piece of the web browser API. Because you're totally right, Kate, we normally would invoke this function, push set timeout onto our call stack. We'd get a new sort of function level execution context for it. However, in this case, what we're really doing when we invoke a set timeout is signaling to JavaScript, hey, I want to do something asynchronous. Set timeout is something that we're going to kind of call a facade function, right? It looks like a regular JavaScript function. It smells like a regular JavaScript function, but unfortunately, it's not a regular JavaScript function. It does technically get pushed onto the call stack very briefly. There is a very brief execution context that's created, but all that that execution context does is passes this task off to the web API. It passes this task off to the web browser. To a particular feature of the web browser API called timer. Ooh. So it passes these two arguments that we pass it out to the web browser API. And so down here in the web browser API, what this is going to look like in our timer feature, timer gets passed a function and a wait. And so when we're out here in this web browser API, we're going to check is this function complete, right? In this case for timer, have we waited the set amount of time that we wanted to? And on complete, if it is in fact complete, what do we want to do? So at this point, not only am I going to introduce this feature or this new piece of the diagramming, which is the web browser API, but I'm also going to start out here tracking our thread and tracking sort of the milliseconds and the amount of time that we're waiting at each of these steps in our execution. These are rough, very just like rough guesstimates, right? But just to illustrate the point, let's say we hit this set timeout at 1 millisecond. Running our code, we hit this set timeout at 1 millisecond. All we do is pass this task out to the web browser API, and then the JavaScript thread is clear. As soon as the web API has taken this task on, our JavaScript thread moves on. Let's say still even at 1 millisecond. Let's say it takes 1.25 milliseconds to do that. So we're still around 1 millisecond here. We move on in regular JavaScript. Out here in the web browser API, we are out here at a roughly 1 millisecond. And at this particular moment in time, right, we have not yet waited the 1,000 milliseconds that we need to wait, right? So in this case, is complete? Nope, not complete. So now we just kind of, the web browser out here is just kind of waiting for our timer to count down, right? Meanwhile, back in JavaScript, what is the next line that we're going to hit in our JavaScript file here, Dennis?
We're gonna console log me first.
So we're gonna hit this console log, and this console log is a function, right? So what happens when we invoke a function?
Get a local execution context, and we push it to the call stack.
Absolutely. So we have this console log where we're passing an argument. We do get a new, oops, that is huge, not necessary. We do get a new function level execution context, right? Our thread goes inside this console log. We obviously don't have the exact function definition for console log in here, so we're just going to kind of hand wave that a little bit, right? But this console log function runs, and then out here at roughly, let's say, maybe 2 milliseconds, we start seeing this first console log of me first, right? And then what happens then, Dennis, when we're done running this function? What happens to our execution context?
It gets deleted and we pop console log off the call stack.
Absolutely, we pop this console log right off the call stack. And our thread then moves back out here into our main thread, or into, sorry, our main execution context, our global execution context. Let's say it comes back out here at around 2 milliseconds. Is there anything else then, Dennis, that we need to run in our global execution context?
We're still waiting for the timer to finish.
Yeah, we're now just kind of hanging out. In our main JavaScript code, right, in our main JavaScript file, we're done running our code, with the exception of this interesting little print hello function that we passed out to set timeout, right? So we kind of just wait, and I'm kind of just vamping here again until we get to a point where now 1,000 milliseconds has passed, right? So out here in web browser land, now, is this function complete? Absolutely. That timer, that delayed functionality, right? That timer has counted down so that we've waited 1,000 milliseconds. And so what do we want to do then when this function is complete, right? What is the delayed functionality that we've attached to this function, Joseph?
You want to return console.log hello?
Well, we want to invoke, right? What we want to
Invoke,
do
yep.
is we want, whoa, what's happening there? Here we go. Let's do that. We want to invoke this delayed function that we passed, right? Which was print hello. So on complete, we want to invoke print hello. And what happens when we invoke a new function, Joseph?
We make a new function execution context.
Absolutely. And I just want to make it clear here real quick. This is, we come out of this console log at 2 milliseconds, but then around 1,001 milliseconds is maybe when print hello actually finally gets invoked, right? So we do get a new function level execution context. And what happens to our call stack?
Is pushed onto the call stack to print hello.
Yeah, the call to print hello gets pushed onto the call stack. And then in print hello, what are we going to do?
Gonna run the console log hello.
Yeah, and what happens when we invoke console log?
We're gonna return hello.
Ooh, do we return hello?
Or
We're invoking a function, right? So what happens when we invoke this console log function?
We push it onto the call stack.
Absolutely, right? Console log hello, right? Pushed onto the call stack. And what else do we get whenever we invoke a function? A new
function execution context.
Yeah, a new function execution context, right? It's going to be a little baby one because we don't actually have a definition for it anyway, right? But that still does happen. We still, right, now at this point, our thread has both moved into print hello and then has moved from print hello into console log, right? I like to illustrate this at this point because this is where we really start seeing value in knowing where our thread is by looking at the call stack rather than just looking at the execution context that we have listed here, right? It's really helpful to now just be able to look at the top of the stack. Whatever the top of the stack is, that's where our thread is right now, right? So it's in print hello, and then around, let's say 1,002 milliseconds, we finally see our hello. Knowing that our set timeout has finished, our delayed functionality is done, awesome, great. And then, of course, Joseph, what happens when we're done running this console log?
It erases the definition, and we're going back to the global execution context.
Are we going back to the global execution context when we're done running console log?
Oh no, we're going back to the print hello.
Yeah, right? So
yeah,
it's
going back
still
to-
technically, yeah, multiple steps here, right?
Yes.
We close out that console log execution, we pop that call off the call stack, and then we move back into print hello. Is there anything left to run in print hello?
No. So we
So what
pop it-
happens now?
We pop that off. The call stack
Exactly. And now where do we move?
back to into the global execution context.
Yeah, totally. So now we're back in the global execution context at around 1,002 milliseconds. And is there anything left now to do in our global execution context?
No.
No. So now we're officially done. Awesome. Thank you so much, Joseph. Sweet. So we've introduced this new concept of the web browser API and some asynchronous functionality here being a set timeout, right? So we have this ability to say, hey, I want to pass off a task to somewhere else so that it's not blocking my JavaScript thread. And I want to be able to continue running JavaScript like I normally would while that other long task is completing. And then I also want to know when that long task is done so that I can run some delayed functionality, right? How do we feel about this? Quick thumbs, people who are on video. We're going to take a quick pause here before we go to the next example. Does anybody have questions about this bit so far?
So this is actually what happens when we do set timeout.
Yep.
Okay. So we would be able to
that set
do.
timeout is actually sent out to the web API, to that timer function in the web API.
So we'd be able to do set timeout, get tweets, and then how do we figure out get tweets, like how long that's going to take?
Great question. We're going to look at the tweet example. The tweet example is going to come back around a little bit later. It's a great question. We're definitely going to take a look at how we can do all of these things together. You definitely can, though. You can add multiple set timeouts if you want, right? If you had multiple set timeouts there, each one would get passed out to the web API. And that's actually a particularly good example, right? Which is where things can go really strange if you don't know how set timeout works. If you've ever tried to use more than one set timeout at a time and you're like relying on these things to be invoked in a certain order or a certain way because you think that they're running like regular JavaScript and they're not, that's where things can get really wonky, right? Because you expect, hey, set timeout, I'm waiting an amount of time, but because I invoked it first and JavaScript can only do one thing at a time, that one will always get invoked first, even if I put 1,000 milliseconds on this one and 5 milliseconds on the second one, right? Not necessarily the case that those are going to be invoked in that order. Great question, Jeremy. How does the browser API or how does JavaScript know that the web API timer is done, right? That is a great question. We're going to talk about that in 1 second. Robin asks, so the 1 millisecond, as per the example, that takes to send the function to the web browser API is the reason why 0 milliseconds would still not work, would still work in this order. Also a great question. That is also what we're going to talk about right now. So let's move on to the next example where we are going to bring this all together, right? And see what actually happens. How do we actually get this on complete back in here to the call stack? Because we kind of just glossed over that in this case, because it was pretty easy to do. Our main JavaScript thread was clear after 2 milliseconds, and we weren't ready to invoke this print hello until 1,000 milliseconds. So it was pretty easy to kind of gloss over how does the web browser know that that this function is done, or how does JavaScript know that this web browser function is done? So now let's talk about some more of the detailed rules that go into getting this deferred functionality back into JavaScript. Because whenever we're working outside of JavaScript, we still need rules in place for getting that delayed functionality back into JavaScript. So let's take a look at this example. It's similar to what we just looked at, but we've got a few new pieces here. In this case now, we've got this block for 1 second function, and we've got a 0 millisecond timeout here. So let's see how this plays out. We're going to introduce some new pieces at this point. It's going to be awesome. Let's go through it. So Peter, tell me, what are we doing? First line here.
We are declaring a function definition in global memory with the label print hello.
Absolutely. What are we doing on the next line?
We are declaring another function definition with the label block for 1 second in global memory.
Absolutely. What are we doing then on the next line?
We are invoking set timeout with the callback print hello function that we defined earlier, the definition of that function, and then a time in 0 milliseconds delay.
Beautiful. 0 milliseconds. Well, I don't need to write milliseconds there, right? 0. And let's say that our thread hits here at 1 millisecond. So tell me then, Peter, what happens when we invoke this set timeout function?
It's going to get passed to that web browser API timer functionality.
Absolutely. Web API, the timer, and quickly just set me up with the component pieces of this web browser API, the timer function. What are we going to do outside here in the web browser?
So it carries over the function definition and the time that we passed in, correct?
Yep. And then it kind of just keeps checking, right? Is this complete? And at, let's say, 1 millisecond when we get out here, have we waited the appropriate amount of time?
Yes.
Yes, right. Awesome. We have, in fact, waited the amount of time that we said we wanted to, which was no amount of time. So what do we want to do on completion of this timer?
We want to run the function print hello.
Yeah, we want to run print hello. Absolutely. So I'm going to pause right there and move back into JavaScript. And let's talk about what happens in JavaScript, right? So we've passed, at 1 millisecond, we've passed this set timeout task out to the web API. As soon as we pass that task out to the web API, our thread keeps it moving, right? Even if it's still 1 millisecond, even if out here, our task is complete when it gets out here, we've already moved on in JavaScript. We've already moved on to the next thing in JavaScript. So tell me then, Yevgeny, what happens next in JavaScript?
I was kind of chatting on the stuff. So we're past the set timeout. That function has been called, and so we're in the next line for block for 1 second. So
Exactly.
We're gonna invoke that function. We're gonna create another functional execution context, which doesn't do anything. Blocks in the JavaScript.
It does. It will. We'll talk about that in a second. What happens though? Also, not only do we create this execution context, but what happens to our call stack?
We push that onto the call stack.
Yeah, we push that call to block for 1 second onto our call stack. And so yes, there is not any specific functionality written in this function, but let's just pretend that there's some code written in there that blocks our JavaScript thread synchronously for 1 second. Yevgeny, do you have any ideas of what kind of code we could put in there that would block our thread?
Sure. You could do a while loop that's endless, but that's gonna block it for a while. But you could do just a crazy incremental integer while like loop or something like that. That's gonna just loop.
Yeah, absolutely. Right. We can have some sort of while or for loop that just kind of loops from 0 to 1,000,000, right? And just kind of loops from 0 to 1,000,000. That's going to take some amount of time in JavaScript for it to do. And so we'd kind of block for about a second, right? So let's say we count from 0 to 1,000,000, and we've roughly figured out, that +roughly takes about a second. So we have some giant for loop in there that does that. So as we're sitting here waiting, plus 1,000 milliseconds, right? 1 second is 1,000 milliseconds. So we wait here. Now, while we're waiting here in JavaScript, let's move back to our web browser API, right? Out to this timer that has already completed and is now ready to run this print hello function. Well, before we said, right, in our last example, we said it was really easy to just not care about how we get this function back onto our call stack because our call stack was empty. But here we can start seeing why we need some very specific rules and mechanisms for getting this delayed functionality back into JavaScript, because what would we do here without that, right? Would we just take this print hello function and just somehow plop it on top of the call stack here within the context of this block for 1 second function? That probably doesn't make sense. That doesn't feel right. Or are we gonna just stop wherever our block for 1 second is and start running this other function? Seems a little crazy. So we have a few new pieces and a few more pieces to introduce here. The first thing is going to be the callback queue. The callback queue is just exactly what it sounds like. It is a queue where things go to wait, right? We have our call stack, which is our data structure that's first in, last out, right? So the first thing that's pushed onto our call stack is the last thing that gets popped off. Now we're talking about a callback queue data structure where things are first in, first out. So the first thing that gets pushed into our callback queue will be the first thing that gets popped off of it or shifted out of it. So when our web browser API finishes doing whatever it's doing and is ready to invoke or is ready to, this delayed functionality that we've passed it, this callback that we've passed it is ready to be invoked, the web API simply takes that function definition that we've passed it, that callback function definition that we've passed it, and pushes it onto the callback queue. So this is print hello, the function definition that was passed out here around roughly 1 millisecond. So it's just sitting out here, waiting in this queue. And then the other final piece that we need to introduce for now is the mechanism that actually moves this function from the callback queue and pushes it onto the call stack. And that is called the event loop. The event loop. The event loop's whole job is to monitor the JavaScript call stack and this callback queue, and only once the JavaScript call stack is completely clear, once we're done running all of our synchronous code, including all of our global execution context, right? Only then will it start draining this callback queue. Only then will it start pushing things onto the call stack from the callback queue. So while this timer function was complete literally the second that it got out to the web API, we still are going to take this delayed functionality, push it onto the callback queue, and the event loop won't push it onto the call stack until all of our synchronous JavaScript code is done running. So let's see what that looks like in practice, right? This function is now sitting out here in the callback queue. Let's go back to JavaScript here. This has been running now for 1,000 milliseconds, and we're ready to come back out here at roughly 1,001 milliseconds. What is going to happen then? Who is running me through this? Yevgeny, right? What happens when we're done running this block for 1 second function?
So then we're going to continue down the thread.
But before we do that, right, what happens to this execution context? What happens to our call stack?
We're gonna pop the function off the call stack.
Yep. Oh, I lost my other bracket there. Yep, and then our execution context goes away, right? Awesome. And then, yep, just keep me going here. What happens next in our global execution context then?
And then we're gonna continue down the next line. We're gonna do console.log.me, .log, and the argument that's gonna be passed down is gonna be a string literal, and it's gonna be me first exclamation mark. Yeah,
me first exclamation mark. What happens when we invoke this console log function?
And then that's gonna create another functional executional context.
Absolutely. What happens to our call stack?
That's gonna get pushed onto the call stack.
Yeah, that call to console log with that argument of me first gets pushed onto the call stack. console log runs, right? We don't have a console log definition right now, but over here in our console then around 1,000 and let's say 1,002 milliseconds, we're going to see me first, right? Sweet. And then of course, what happens when we're done running this function here?
So I guess then the callback queue takes over. And
Yep, but what happens when we're done running a function?
So then yeah, we have to deallocate the executional context, the
Yep,
functional.
and pop it off the call stack, right?
Yep, that's right. Pop it up. Yeah.
Sweet. Thank you so much, Evgeny.
Yeah, you got it.
So we are here then, right? At around 1,002 milliseconds. We're out here, and now we have no more synchronous JavaScript to run, right? The last synchronous piece of JavaScript that we had to run was this console log of me first. So now our event loop sees that our global thread is clear. There's nothing else that's going to get pushed onto the call stack from our synchronous code. So now it starts looking at the queue and says, okay, there is in fact something in the queue here. So now I can actually pull this function off the callback queue and push it onto the JavaScript queue, or the JavaScript call stack, not the queue, right? So print hello finally gets pushed onto the call stack. What happens when we push this function onto the call stack? Kate.
Then we're gonna have a new function level execution context, print hello, and then
Really?
we're gonna invoke inside. We're gonna invoke console.log hello.
Absolutely. So we have this new function execution context for print hello. Print hello then invokes this console log. And what happens when we invoke this console log, Kate?
We have a new function level execution context of the console log hello, and then we push console log hello to call stack.
Absolutely, we do. Awesome. And then, of course, console log somewhere over here around 1,003 milliseconds, we see, hello. And then what happens, Kate, when we're done running console log?
And then the console log hello is go away. The thread of execution go back to print hello. The console log is pop off. And then now we inside print hello. Then we there's nothing else to run. Then we exit print hello. Go back to global execution context. Print hello got pop off the call stack.
Beautiful. Thank you so much, Kate. Amazing. Yes, exactly. So now that we finished running print hello, we finished running that console log, right? We're back in our global execution context again, right? But now we're completely done, right? There's nothing left in that callback queue. There's nothing left in our synchronous code. Now we've completely run, right? But let's take a quick look at this before we move into more questions, right? Let's take a look at this. We initially set out to run this set timeout and wait 0 milliseconds, and yet it took until 1,003 milliseconds before we actually saw that print hello function, you know, the actual meat of what we wanted to do, printed to the console. This right here, this sort of side effect right here is why a lot of people have trouble with set timeout. Because a lot of people look at set timeout and think, okay, what I'm doing is setting a timeout. And so what I'm saying, the arguments that I'm passing in here are wait this amount of time and then invoke this callback function. It's a pretty reasonable assumption if all you're familiar with is how JavaScript works. And you think, rightfully so maybe, that set timeout is like any other JavaScript function, that it works the same way that any other JavaScript function does, right? Unfortunately, that's not the case, or sort of fortunately, that's not the case, right? Because if this worked synchronously, it would be really annoying if you were waiting 1,000 milliseconds and couldn't do anything else. Excuse me. What we're really saying here with set timeout is we're saying set a timeout, wait this amount of milliseconds before this callback function is ready to be invoked. Only invoke this function, another way of thinking about it, only invoke this callback function after at least this amount of time has passed. So we may never really be exactly sure when this deferred functionality is going to be run. It's something to keep in mind, particularly if you're going to use set timeouts, particularly if you're going to use a lot of set timeouts, or set intervals work the same way, right? Anything that's being pushed out to the web browser API, you want to understand that time works a little bit differently there, right? In that the way and the mechanism that we use to get this delayed functionality, this delayed functionality back into JavaScript, right? Back onto the call stack is a little bit different, right? We may be waiting a longer amount of time than we think we are before that functionality gets run. Okay, let's pause here and take questions. Anybody have questions? Let me know. Yes, 100% Jose. So no matter how much this timeout is set, it'll be executed at the end, whether it's 0 or 1,000,000, absolutely, maybe 1,000,000. I didn't count all the zeros you had there, but yes, regardless of how much the wait time is, we are always, always, always going to, at the very least, wait until all of our synchronous code has run. Now, it might be that we'll get lucky, right? It might be that we'll get lucky, like we did in this first example, where all of our synchronous code will be run and completed well before our timeout is done. And so our delayed functionality will get pushed on and run roughly, right, around the time that we expect it to, right? Wait 1,000 milliseconds, then run. So having it run at around 1,002 milliseconds, pretty good, right? But it's equally likely, and maybe even more likely, that we will already have our thread blocked at that point in time. And so we'll have to wait a pretty decent chunk of time before that actually runs. Todd asked, can you have multiple functions in the callback queue? Absolutely you can. Same way that you can have multiple calls pushed onto the call stack, you can have multiple things sitting out here in the callback queue, and they'll be run in the order in which they were pushed in, right? Because that queue data structure is first in, first out. So whatever the first thing is that gets pushed in there will be the first thing that gets run. As soon as that's gone, this item gets moved, right, to the head of the line. And then we pop that one off or pull that one off, and then we have one left, and then we get that one off, right? So you can have multiple things sitting out there. Oh, go ahead.
So really the only thing, the time piece of the set timeout, so if you have multiple set timeouts, it really just decides how they're going to line up in the callback queue, right? So like if you had something that's 1,000 milliseconds versus 2,000 milliseconds, obviously the 1,000 millisecond will be first in the callback queue versus the 2,000 millisecond, correct?
Probably. So I'm never going to say always or definitely, right, for the most part with those kinds of questions, because it does depend on, you know, maybe you know, if they were invoked one right after the other here, like if this was a set timeout of 1,000 and this one was you know, 500 or whatever, right, then probably yes, that 500 would get pushed onto the callback queue first. But there's always some amount of uncertainty when we're doing these asynchronous things for multiple reasons, not only because we're potentially pushing it out there later, but also because even in C++ land, which is what the web browser API is running on, we don't have infinite amount of threads to work with. So we can't do an infinite number of things at the same time. So just kind of keeping that in mind, that there may still be things out here in web browser land that are not running at the exact same time.
Okay.
quick question.
Yeah.
Is set timeout the only way to access the API, the browser's API?
Definitely not. I
Okay.
think the next example that we're going to look at has another way of dealing with the web browser API and pulling out the web browser API.
I have a question.
Totally.
This might be a little bit more. You know, it's funny because I made a backend with Node using WebSockets, and I used set timeouts, and I was getting such strange ping like packets back and forth in the times. I couldn't figure out why that was happening, and I realize now because it is single threaded and it's going through its own thing, and you know it's in a queue, and but like, so how do you fix that without not creating other threads for your connections and whatnot?
So yeah, so that's a very specific kind of implementation specific thing. I'm happy to chat afterwards about more specific cases like that. It honestly is going to depend, right? In that particular case, it might be really tough to resolve those things. My first question would probably be around like why you're using a set time, like what your use case for that set timeout is. But we can, and I'm happy to, you know, kind of chat afterwards a little bit more about that particular use case. But a lot of times for these things, it's going to be about first, right, recognizing that this is what the problem is, right? I'm sure without knowing that these things are getting pushed out to the web browser API and then going through a callback queue, that it's probably really hard to debug that if you're thinking that this just runs as regular JavaScript, but you're getting all these packages sent maybe at one time. And so a lot of it is just knowing that that's what's happening, and then you can kind of assess from there and figure out, is there just a different strategy that I need to employ here? Is there a different way that I need to go about getting these packages sent at a later time or a later date? But yeah, it's a good question. It's just going to be more implementation specific, so going to be hard for me to answer right off the top right now. Okay, couple more questions here in the chat, and then we're going to move on, but we'll come back around to questions at the end. So yes, you'll be able to rewatch this workshop later. It may not be this particular recording, but this workshop is up on our YouTube channel for you to watch at your leisure anytime you'd like. Is this why we sometimes see a message if the page is not shown in 5 seconds, click redirect? Interesting. That's a question I haven't gotten before. Possibly. Yeah, it's totally possible that something like that is due to, you know, asynchronous timeouts or something like that. It's possible that we have requests that get timed out after 5 seconds, and so we just want people to either click the redirect link explicitly or just give people the option to do that. That's probably one reason that that's out there. Yeah, there's certainly asynchronicity behind that. Wait 5 seconds for the redirect. Whether that's why that message shows up or not, I'm not 100% sure. But for sure that is something asynchronous happening in the background.
Also,
Great question.
I have another question regarding the second parameter, the time. So assuming that theoretically, if we put the set timer function in order, so does that mean that technically whatever time that we put in the millisecond slot, it actually doesn't matter because it actually follows the queue anyways?
Sorry, I'm not sure I totally followed that. Give me like an example of what you're asking there.
So like in this previous example that we did, that the fact that the set timer it's supposed to execute the print hello function after 0 millisecond. Technically, if the asynchronous features that's in the global context, if that's going to take more time than the 0 millisecond, then technically you can just put whatever time on there because it wouldn't matter, because the code that's after the set timer will have to finish executing anyways.
So sort of. I'm still not 100% sure I'm with you, but let me try to parrot back to you and see if we can figure out if we're on the same page here. So basically you're saying if I put any number here, if I put 100 here, it won't make a difference in this particular case because it's the only set timeout, and it's going to have to wait until all of this code gets executed anyway. Is that kind of?
Yeah.
So yes and no, right? in this case, right, if I put 100 milliseconds here, it probably doesn't matter, but it definitely matters if I put, if I put 2000 milliseconds here. Because now if I put 2000 here, and we can like kind of track through the rest of this, we'll be technically ready to run this function after 1001 milliseconds, but we've now put a timeout of 2000 milliseconds here. So our timer at this moment would still not be ready. So it would still wait another, 999 milliseconds
Right.
before it runs. So, so again, it kind of depends on what your use case is, how sure you are of, how long it's going to take for that thing to run. So yes and no, right? Putting a zero probably, like, putting a zero really doesn't mean run it right away, right? In that case, you might as well just run print hello.
I guess my question is actually like what I'm seeing is that there's no obvious disadvantage of just putting the time 0, because basically you want to wait and then you want to run it after whatever that's in the queue before it anyways. But is there a potential disadvantage of putting 0 for all of them in case that there might be some kind of a collision in a sense?
Yeah, so okay, yeah, let's be clear here, right? Putting a 0 here isn't necessarily going to push it to the front of the queue, right? If there was something already sitting out here, and this was a wait of 0 milliseconds, that print hello would still be on here after that, right? It doesn't force it to the front of the queue in any way. If we had multiple set timeouts here with a wait of 0 milliseconds, that's gonna go out to the web browser API to determine in what order it's gonna push those things onto the callback queue. That's gonna be something in kind of C++ land, which is the language that the browser is built in, and that's running this web browser API. That'll be up to however the web API is set up to handle things being kind of done at the same time. But it's unlikely that you'd have things done at exactly the same time, because remember, you're still waiting some amount of time for each line of these in JavaScript, right? So set timeout still has to wait until it pushes it out to the web API before it would move on to that second set timeout, right? If we had another one here, it would still need to wait until this first one is at least pushed out to the web API. So it's probably really unlikely that you're going to get 2 items that are done at exactly the same time and have some sort of collision like that. They're more likely than not going to be pushed on at different times, even if it's just slightly, points of a millisecond off.
Okay, thank you.